Hi, my name is Brittany Yeshua. I'm the president of Burke Aerospace. Burke Aerospace is a manufacturer of both aerospace and industrial gas turbine components. I think about it, from the military side, but also the commercial side. I fly on those planes. My family flies on those planes, and I want to know that every single part is 100% conforming and safe, and to know that we can bring our soldiers home safely. The benefits of model-based definition, you're taking lead times that would primarily take, 3 to 6 months on an NPI cycle down to 1 to 3. This morning I walked in and our engineering team, who were wonderful, knew that I was going to be talking about model-based definition. And he said, look at this, we just had a model come in. He's like, I'm already starting the program now. So I saw firsthand this morning how quickly, we go from, concept to production, just got cut by 2 months just with that one model being presented in that format. You need to make sure you have invested in the equipment to be able to absorb those files. There's things out there that will allow you to add on to your machine's existing equipment, but you have to make the investment to make sure that that data can be transferred easily between the two. We did a business case and we looked at it. We made our money back within the first 30 days. And that's amazing for a payback. We already invested in both the monitoring and censoring on the machines, but we also invested on the inspection side of it as well, because it's full circle. You need it all reading to one another. And so it really takes the human out of the rework. A lot of times you'll see the non-conformances happen when you try to rework a part. And this takes the whole reworking loop out of the picture. The information would be shared between the inspection report and the machine so that they can go on and make offsets without having to pull a human into the process with taking the part out of the machine to inspect it on something else. Take a lot of that guesswork out. At the end of the day, make a more conforming part with less defects.
As you heard from Brittany at Burke Aerospace, their company is taking full advantage of model-based definition. They're able to get their parts out to market much faster with less cost, but more importantly, increased quality. I'm Jackie Garofano, Chief Technology Officer at CCAT, the Connecticut Center for Advanced Technology. We've brought to you a series of videos all about model-based definition. In our first video, we showed you how to create that MBD file. And in our third, it's all about inspection using MBD. Now, we're going to take you through the process of creating CNC toolpaths to machine using this DMG Mori.
Thank you, Jackie. So at this point, I'd like to go ahead and open up my model-based definition file, set up my machining environment, and the best person for me to talk to in order to accomplish that is my colleague, Henry, who's an applications engineer.
Henry, sir.
Hi, Henry. So I have the part open here on the screen, and I've got 3 basic dimensions on the part, which give me an idea about the size. Looks like the height is 1.75 inches, the width is 6 inches, and the length is 9 inches. And the material that's specified for this part is aluminum 6061 T6. Do you have any recommendations on the stock material size, the kind of machine that we should put this on?
So for the blank material, I would go with material that's slightly larger than the final part. So I have this part here that's about 6.5 by 9.5 by 2 inches.
Okay.
As far as the tooling goes, it looks to me like there's nothing too special needs about tools on this part.
Okay.
As far as the type of machine to go with this, a 3-axis machine would be fine, but we have a 5-axis machine ready to go that we'll put it right on there.
Okay, great. Well, with that information, I'll go ahead and set up my environment within SolidWorks CAM. Thank you.
Cool. Thank you.
Now that we have the information about the tooling that we're going to use, some idea about the stock material, and about the machine that we're going to put it on, we can go ahead into SolidWorks, and we can put all that information and set up our environment for the machining. I've got my file open here, and this is the model-based definition file that we had created. All of the definition is on each of the features here, and we're going to use that to our advantage. What we're going to do is, the first thing is go into SolidWorks CAM, and we want to go into defining our machine. And in this case, this part, as Henry pointed out, is 3-axis machining. The post processor, the particular machine that we're going to be using is a DMG, and that uses a numeric 840D control. So we're going to be selecting a Siemens 840D control from the options here under active post processor. We don't need to set up a rotary axis. We don't need to set up the tilt axis. We're going to strictly maintain 3-axis machining on this part. So with that set up, we're going to go ahead and click OK. And then we can get into our tools dialog. If we hover our mouse over the top tabs, you can see that one of the tabs is SolidWorks CAM Tools tree. If I select that, I have a number of the tools already defined. And if I wanted to add more tools to it, for example, let's add in a 1/4-inch flat end mill. We'll go ahead and right-click on the DMG machine, and we'll add a new tool from library. And what we could do here is we could select a flat end mill, and we can scroll down to where we find a 1/4-inch, and we're going to choose a 2-flute and hit OK. So you can see there that that's added my 1/4-inch flat end mill to my tool set. At this point, we can go ahead into our SolidWorks CAM feature tree. And at this point, we can set up our stock manager. We go to Edit Definition. We know that this material that we're going to be cutting out of is aluminum 6061 T6, so we can define that here. I already have it defined, but we can go ahead and just drop down the dialog, and you can select 6061 T6. That's an aluminum alloy, and our stock type, we're just going to choose a regular bounding box. So you can see here the different kinds. Our part is pretty rectangular in shape, so the bounding box method is going to be fine for generating the stock material. We can choose our coordinate system here if we had one defined, and then we can define our bounding box offset. So we can add a little bit of material on each side, and you can see what I have defined here. 100 thousandths on X and Y, and then on Z I have 400 thousandths added. You can go ahead and click the checkbox here. The next thing we want to do at this point really is, because we have defined now our environment, we have defined all the tolerancing per feature, we want to go into SolidWorks tolerance-based machining dialog, and we can set up our strategies. So if you go into the SolidWorks CAM tolerance-based machining tab, you'll find two different options. There is a tolerance-based machining run and tolerance-based machining mill settings. So since we already have this defined as in the units to be in inches, we're going to go ahead into the settings dialog, and you can see that there's a number of items that we can really set up here. The first one that comes up is the tolerance range, and we're going to switch over to inches. You can see all the different features that SolidWorks CAM can recognize. What we can do here is, for each of the features that it recognizes, we can set up a number of different tolerance ranges, and for each of the tolerance ranges we can set up the machining strategy. So for example, for hole, what we're going to do is, if we click on it, you can see down here that it already has 3 tolerance-based conditions defined. If we click on the Edit button, we can change the ranges. So in our case, what we want to do is we're going to go ahead and just delete, type in 5/10 thousandths, and we can click on the add, and then we can add in another range of 5/10 thousandths to 1 thousandth. So we can go ahead and just type in 1 thousandths, and then from 1 thousandths to 7 thousandths, and we can add that in. Click OK, and now you see that my tolerance ranges have changed. And what I can do at this point is modify the strategy. So we have 3 different strategies per tolerance range. One of the biggest time consumers in coming up with machining paths is when you're dealing with asymmetric tolerances. Using tolerance-based machining, you can save a ton of time because the system automatically detects asymmetric tolerances and automatically applies machining offsets so that you're machining to the mean. In this case, we're going to use tolerance-based machining inside of CamWorks that automatically calculates all the machining paths to the means of tolerance. And what we're doing now is we're going to be setting up the undersized, the nominal strategy, and then the oversized strategy. So within SolidWorks CAM's tolerance-based machining dialog, for each of the features that we see, you can see that we have those three strategies. So undersized, if you have a minus 5 thousandths plus 0, you would be on the undersized strategy. If you had a plus 5 minus 0, you'd be on the positive 2.5 thousandths strategy. Whereas if you had a plus and minus 5 thousandths, you'd be on the nominal strategy. And so what we can do now is we can set up our machining strategies here. So for a loose tolerance, we're okay with just doing a drilling operation. So we're going to just go ahead and select drill for all three, for undersized, nominal, and oversized. If we have a slightly tighter tolerance, we'll go in with a reaming operation. And then if we have an even tighter tolerance, we'll define that as a single point boring operation for all three of the strategies. In the same way, we can set up our strategies for countersink hole, for rectangular pockets, for irregular pockets, and all the other features that you see defined here in the list. The other strategies that we can set up are our GD&T. If we click on the tab in the dialog here, you can see that for each one of those features, we can also set up our strategy for the different GD&T callouts. So for example, if we have a irregular pocket and it has a cylindricity callout or a profile of a line callout, we can set up our different tolerance ranges per symbol, and then we can set up our strategy for each one of those symbols. So with that being all set, the next thing we're going to do is just go ahead and click OK. We've essentially set up our tolerance-based machining strategies using the dialog, and you saw how simple that was. It's you just give it the information that you typically would take looking at a 2D drawing and deciding on the best tool, the best machining path, the best strategy to use to produce that part. It's a one-time effort, which you can periodically update if you find that other strategies work better over time. But essentially, once you have this set up, every time you receive a model-based definition file to create a machining path from, the system reuses all of that information that you've recorded. So it, in essence, knows and has the logic of what decisions to make to apply the correct tooling, the correct machining paths, the correct strategies to produce that feature. You're saving a ton of time here. If you had one feature, you may see that if you did it manually versus using tolerance-based machining, maybe the time savings isn't that much. But when you have 200-300 different features, you're saving a lot of time. So the more complex the part is, the more beneficial this system is for you. In order to execute, what we're going to do is we're going to go ahead over to our tolerance-based machining run button. And what we want to do is we want to specify under the options that we want to recognize tolerance ranges. So I've got that checked on. Since that's checked on, you could see here that if I switch over to my tolerance range, all of my strategies are listed here. And you could see that the number of identified features are 0. So nothing is recognized yet. What I have to do is go down and click on Extract Machinable Features. Now that that function is finished calculating, you can see that for the whole feature, we have 1 of 1 recognized. And you can see that that hole is highlighted here on the CAD model. For irregular pockets, you can see that we have 2 of 2 identified here, rectangular slots. Now, one of the things that I want to point out is the different strategies for each of these features. So if we click on, for example, irregular pocket, we can see down here in our tolerance ranges that we set up prior that we have 2 pockets identified, and both of which fall within the 2000s to 1000s tolerance range. And these are these 2 pockets here. And if we take a look at the tolerance ranges for each one, on this particular pocket, I have a width call out of 1 inch plus 3 thousandths minus 1 thousandths. So in this case, we're going to be using the oversize strategy to machine to the mean. And you can see that in the tolerance-based machining dialog, it's identified that one of the two features is on the oversize strategy. If we look at the other pocket, we can see that this one is plus 2 thousandths minus 3 thousandths. So that would fall under the undersized strategy for machining to the mean. And you can see that in the dialog, it has identified the other feature to fall under the undersized strategy. So in this case, both are rough finish, and this is the true power of the tolerance-based machining. It will automatically recognize the tolerance ranges attached to each of the features, and then it will come up with the appropriate strategy to make sure that you machine to the mean. So I'm going to go ahead and click OK. And you can see that I have a mill part set up here. If I hover my mouse over it, you can see the preview of those operations. And what I can do now is right click, and I can generate an operational plan. And now that my operational plan is all set, I can go ahead and generate my toolpath. So now if we step through this, you can see that I have a SolidWorks CAM automatically came up with a rough milling path for my perimeter and the appropriate tool for that path. Then we have a contour to finish off that perimeter, a roughing path to eliminate a lot of the stock material from the top face, contouring around all the bosses on the top of that feature, rough milling to get rid of the material on the outside of the part, contouring again, this pocket, we've got a cutting path defined on it, a path to cut out this notch on the back, and you can see the two pockets as well. So we're going to go ahead and simulate this. To make sure we don't get any gouges or crashes. So Henry, I see you've got the stock material in the machine.
The only thing I would need from you would be the machine coordinate system, the origin offset.
Okay. Henry, that looks great. Yeah, the surface came out nice and smooth. Kind of anxious to see what the measurements are on a couple of these features before we take it over to final inspection.
Nasir and the team have shown you how to create an MBD file, automatically ingest it into your machining operation, and now it's time for inspection. Leveraging MBD saves your company time, cost, and most importantly, puts your parts out to market faster. And that's what we're going to show you in this next video.